Hey guys, welcome back. Let's look at a quick application of the central limit theorem with flipping a coin, and then we'll move right into the assignment. So it should be pretty simple today. So let's say that we flip a coin 10 times. So out of our 10 coin flips, we would expect on average half of them to be a heads, right? But it wouldn't be very unusual to have 4 heads or even 6 heads or even 7 heads out of 10, right? Even though it would be 70% heads, because it's such a small sample, there's going to be a lot of variation that's left over in the sample. Now, instead of looking at this as a binomial, which is out of 10, how many heads would we expect, which would be here, we could also look at this as proportions, which is what we started to look at the other day. So all we're going to do is divide everything by n, which is our number in this case of our trials. So if I take a tenth of all these values here, it's pretty simple. That's why I chose 10. So just moving the decimal over 1. So 50% of the time, 50% heads would be this bin here for our histogram. 60% heads would be 6 out of 10. 70% would be 7 out of 10, etc., etc. All right, now what happens as I increase the sample size? So this would be basically a sampling distribution model centered at 50% with our proportion with a n is equal to 10. So these are samples of 10 with a probability of 50-50. What if I increase the sample size? So if I increase it to 25 in this case, what's going to happen is it's still going to be centered at 50%, but the standard deviation is going to narrow. It's going to be there's going to be less variation from sample to sample because we're now taking means or averages of larger numbers in this case, or proportions. And all right, so of all the possible samples that we would get, now it's going to be much more narrow. So if I basically drew these lines going down here, the same proportions would be here. So 40%, 40%, 60%, 6%. So now it looks like that we're going to have much more of our distributions are going to be within 10% of the mean here. So our standard deviation is actually, instead of going to be 15 or 16%, it's actually now going to be 10%. So it's a little bit more than half. Okay, but now let's say that we increase our samples. Instead of samples of 25, now we're going to do samples of 100. So I'm going to quadruple my sample size. So now what's going to happen is now there's going to be even less variation. So it's going to be even tighter or even closer to the mean of 50%. In fact, now it's going to be 2 standard deviations out what would be considered unusual would be anything more than 40 or 60% proportion of heads. So we went from having a lot of variation because we had small sample size. As we increase our sample size, the variation is going to shrink. But it's going to do that by a law of diminishing returns. And what we notice here now with our standard deviation, instead of dividing by n, which is 25, when we multiply that times 4, 25 times 4 is now going to be the square root of basically 1/4, which is half the standard deviation we had before. So instead of 10%, now we have a standard deviation of 5%. So essentially, whenever we quadruple our sample size, our standard deviation will be cut in half every time we do that. So it is what we call the law of diminishing returns. So these are for I graphed out 3 different probabilities of success: 50%, 25, and 10%. The largest standard deviation is going to be with 50-50. That's like our worst case scenario. So that's going to be the highest one. As we get further away from 50-50, the lower our standard deviations are going to be. So with the binomial, the standard deviation was a square root of n times p times q, meaning as n increases, so does our standard deviation. But when we're dealing with proportions, when we divide the n times p times q by n, remember we were able to take the square root of this squared, and then we were able to take out the n, so basically put it under the radical. And now whenever n is increasing, it's now in the denominator, so it's going to decrease the proportion. Even though the total number of heads that we have are going to be, the standard deviation of the number of heads is going to be increasing, which is a binomial, the proportion, when we divide it by the total number that we're doing, is going to be increasing at a greater rate, and so it's going to, one's increasing by the square root of n, the other one's increasing by n, so it's increasing by a greater rate. The limit as n approaches infinity if you know the calculus, but it's okay. So essentially now it's going to be graphing this out here. So then when we quadruple our sample size of 400 again to get to 1600, it's going to half it again. So we have to basically quadruple our sample size, or multiply our sample size by 4 in order to decrease the standard deviation by 1/2. So we do get this law of diminishing returns, where after a while, I mean, we're going to have a really large sample size in order to be able to cut it in half again for a standard deviation. So keep that in mind. All right, so number 3, we're basically starting on the assignment, the AP exam. So a small class of 5 students receives the following scores on their AP exam. So a 5, a 4, 4, a 3, and a 1. Graph the histogram of the population to the right. So the population is going to be basically all the scores that we have here. So we have 1 5, we have 2 4s, so that'll be there, and then a 3. Didn't mean to do that one. A 3 and then a 1. So there were no 2s in this case. So that's our population. That's basically if we took a census of all the people who took the test, all 5 of them, we got it. So the next thing we're going to do is we're going to do a sampling distribution model where we're taking the average of 2 scores. So the average for this one, if we put it in the calculator, so let me pull up my calculator real quick. Basically, we can put all these data into list 1 and then run a 1 variable stats, and they'll give us the mean and standard deviation for that. So let me go to stat. So yeah, it's fine. So stat edit, and I'm going to put all of this data in here. So we have 5, 4, 4, 3, 1, and I'm going to delete this one here. All right, so for list 1, we're going to now run, I'm going to go to stat and then calculate 1 variable stats on list 1. We're not going to use a frequency list on this one, not doing our discrete random variables anymore. And our mean is going to be 3.4 with a standard deviation of 1.51. Now we do need to take a look at the different standard deviations you have here. One of them is the standard deviation for the sample. One of them is the standard deviation for the population. So basically the population is if we are looking at the entire group. So we have a census in this case. It's not a sample. We knew all 5 of the scores for all 5 of the people in that class. So that's actually the population. And whenever we have the population, which is rare that we would be able to take a census instead of a sample, but we actually use the sigma of x. And on a lot of calculators, they actually don't even give you this value, or a lot of programs you have to put in something special in order to get that, because it's so rare that we have the entire census and we're not taking a sample. We almost never know the population. So basically we have population in the sample. So in our previous example, that'd be like all the possible M&Ms would be the population, and a sample is going to be whatever you have access to in class or something like that. So the difference between these 2 letters is this is the Latin letter S, and then this is the Greek letter for S, which is sigma. Now Greek, the Hellenistic culture came before the Roman culture, the Latin culture, and so one way you can remember it is that the population goes with the Greek because that became before, and the sample came after the sample of the population, which is Latin. So our true proportion is going to be P, our sample proportion is P hat. The standard deviation, which is the sigma of X, is the standard deviation from population, where the standard deviation of the sample is going to be the S of X. So almost every time we're going to use S of X for standard deviation, but in the rare case we have a census like we do now, we're going to use the sigma of X, which is going to be 1.356. So we have 1.356, and our mean was the X bar, which is going to be 3.4. So we're centered at 3.4 with a standard deviation for a population of 1.356. All right, the next thing we're going to do is we're going to find the sampling distribution model when we take samples of 2, or averages of 2. So I just need to pair these off in all the possible combinations of 2 that you could have. So I have 5, 4, 4, 3, and 1, and 5, 4, 4, 3, and 1. And basically where these intersect, that's going to be I'm going to put the sums there. So 4 plus 5 is going to be 9, and then 4 plus 5 again is 9. 3 plus 5 is 8, 1 plus 5 would be 6, and then 4 and 4 is going to be 8 again, then 7 and 5. Then here we'd have 3 plus 4, which is 7, 3 plus 1 is 5, and then 3 plus 1 is going to be 4. That was 4 plus 1 in the last one. Anyway, so the red numbers here are all the possible sums, so all the combinations of picking 2 that it could have. And again, this is not really sample, it's a population, or census is a better way of saying it, because we're getting all the possible combinations, not just randomly sampling them. So we're going to be thorough and basically evenly distribute them, which is kind of nice. So I need to take the average of all these values. So I'm going to put them in the calculator and then divide them by 2. So I'm going to go to stat, edit, I'm going to put all these in list 2. So I'm going to do 9, 9, 8, 6, 8, 7, 5, 7, let me try that again. 7, 5, and then 4. There should be 10 of them. There are. Okay, so I did it right. And then for list 3, I'm going to do the average of list 2, so I'm going to divide those by 2. I think I actually had you do it differently, so let me change that. So for list 2, I'm going to hit enter, and I'm going to redefine list 2 as half of the previous list 2. So I'm going to click clear here. I'm going to define list 2 as list 2, so second 2 divided by 2. Then hit enter, and basically it's just going to cut them all in half, which is nice. Now I want to take, these are the average of the sums, all the possible sums, and I want to take, I'm going to graph this out and then find the mean and standard deviation. So another thing that might make this easier is if I sort this list. So let me quit out of this, and then I'm going to go to second list, go over to operations, and then I'm going to do sort ascending, and then sort list 2, so second 2, and then hit enter, and that'll sort the list. So then go back to stat and edit, and now it's listed in ascending order. So my lowest one I'm going to have is 2, so that's going to be right here, and then we're going to have 2 2.5s, and then we're going to have 1 3, and then 2 4s, 2 3.5s, and then 2 4.5s, and that's going to be our largest ones there. So this is our histogram for the samples of all the possible means of samples of 2. And then I want to find the mean and standard deviation for that one, so I'm going to go to stat, arrow over to calculate, one variable stats. Now I'm going to do list 2, so that's going to be second 2. Don't do a frequency list, then hit calculate. So we still have a mean of 3.5. Now our standard deviation, which again, remember we're going to be using the sigma, is going to be 0.83. So pretty much the same thing. And then notice what happened. So it's still centered at the same mean of 3.4, but now our standard deviation is shrinking. That's kind of the same thing we saw with as we increase the sample size of with the samples of flipping coins, right? Our mean is still going to be centered at 50%, the true proportion, but it's going to start to shrink, and that's the central limit theorem in action. All right, so there's one more that we want to do, which is all the possible averages of 3 of those values. So I listed out of the 5 choosing 3, and these are all the possible ones that you could have, and I even listed the sum for you. So all we have to do is put in list 3 the sum, and then list 4 we're going to divide these by 3 to find the average for those. So go to stat and edit, and then for list 3 I'm just going to put all those in there. So we have 8 8 9 9 10 10. I'm pretty sure we have 2 11s, so 11. Oops, that's not a 10. Alrighty. Now I'm just going to move this to the side so it'll be easier to see. There you go. Alright, then we have 111, 112, 112, and 113. Alright, and our list is the same list length of 10, which is what it should be. Okay, for list 4, I'm going to arrow over it and then hit enter. I'm going to define list 4 as list 3 divided by 3. So actually, I'm going to do alpha x, and then that is going to be a shortcut for numerator over denominator, and then I'm going to do list 3 over 3, and hit enter, and that's going to give me as fractions, which would be nice and easy because I'm graphing them as fractions here, because everything was divided by 3. So at that point, I'm going to just kind of go through those. So how many 8/3 did I have? Looks like I've got 2 of them. So you can fill those in. So basically this is 8/3, 8/3, and then 3, 3, 10. The reason we need to put it in the calculator is because that's how we're going to find the mean and standard deviation. So we don't need it to graph it. Obviously we know how to divide it by 3. So we had 2 8/3, so that's going to be 7/3. 8/3 would be right here. So there were 2 that were here. Should be, there we go. So we had 2 8/3, 9/3, which is just 3, and there's 2 of those. 2 10/3, 1 11/3, and then 2 4/3, or sorry, 4s, which is 12/3, and then 1 13/3. Okay, what is interesting here is by choosing out of 5, choosing 2 is the same thing as not choosing 3. And so what's interesting is these averages that we see. This is symmetrical about this mean, which the mean would be at 3.4. So right down the middle, all these have the same mean of 3.4, and see if you notice this pattern here is just reflected across the mean. It's fascinating how that works, but it kind of makes sense, like a little bit. So let's put this in the calculator for list 4 and see what we get for one variable stats for list 4. So stats, calculate, one variable stats, second 4, then hit calculate, and still centered at 3.4 like we would expect. And now our standard deviation is going to be 0.55, 0.554. Okay, cool. So again, as we increase the sample sizes, the central limit theorem is going to kick in, and it's actually going to become more nearly normal, which is kind of cool. But also what's happening is that our standard deviation is going to be shrinking, just like we observed before with this right here. So as we increase our sample size, our standard deviation is going to be, because we're dividing by the square root of n, our standard deviation is going to be shrinking as well. We're really kind of honing in and removing more variation and honing in on the true proportion, or in this case, the true mean, which was 3.4. Okay, cool. Awesome stuff. All right, so this is central limit theorem. This is another example. This one's with dice. So if we just look at the average of one dice, basically just what's the probability of rolling a 1 or a 6, that's unimodal, right? Or sorry, not unimodal. That's uniform. It's the same probability all across the board. Now, if we take the average of 2 dice, that's where our triangular distribution comes in. Then if we take the average of 3 dice, now it starts to look more nearly normal. And then the average of 4 dice, even more normal, and our standard deviations are going to start shrinking. If we did 20 dice, you can even look at the book, and it's very skinny. It looks a whole lot like this one down here, which is kind of cool. All right, let's get started on the assignment number 27, polling. Just before a referendum on the school budget, a local newspaper polls a random sample of 400 registered voters in an attempt to predict whether the budget will pass. Suppose the budget actually has the support of 52% of the voters. So, do you think the appropriate conditions are met? So, the sample of 400, they said it was a random sample, so we will assume that it's representative because they said it was random. 10% condition, so as long as we're sampling less than, because we're sampling without replacement, it's not truly independent, so as long as we're sampling less than 10% of all the people who are going to vote, then it's okay because the probabilities will change, but they'll change so slight it won't change our end results. So as long as we have more than 4,000 people who are going to vote, then we're sampling less than 10%, so we're good to go. Success, failure, this is to make sure the normal model is appropriate, so that we have a large enough sample. We have to have at least 3 standard deviations on both sides, and that's guaranteed if we have at least 10 successes and 10 failures. Well, out of a sample of 400, if we're expecting 52%, that's going to be 208, which is way more than 10, and going the other direction, that would be 192, which is also way more than 10 failures as well. All right, so it is appropriate to use a normal model. This is a sampling distribution model. So the sampling distribution model is basically when we know the true proportion, which is going to be 52%. This is all the possible samples that we could get of size 400. And what kind of proportions would we expect to get from that if the true proportion was 52%? So it's going to be centered at 52% with a standard deviation of, let me pull up my calculator here. And I'm going to quit out of that. So that's going to be 0.52 times q, which is 0.48, divided by our sample size of 400, and then we're going to take the square root. It's a very small number. So caret 0.5, which is going to give me basically 2.5%. So a standard deviation of 2.5%. Okay, so fill that in. We want to know the probability the newspaper sample will lead them to predict a defeat. So defeat would be if you had less than 50% from our sample. So we're going to go in this direction over here. And of course, this one does not like to work for some reason. I still haven't figured out what's going on there. So anyway, 50%, which would be a defeat, which would be just slightly less than 1 standard deviation below the mean. So we want to find that area under the curve. Let me try that again. Going up to 50%. So we're going to go from negative infinity all the way up to 50%. We are using a normal model centered at 0.52, which is our proportion, with a standard deviation of 2.5%. Now, instead of going from negative 999, which you totally could, we could actually start at 0, because if we're dealing with percentages, the lowest percent you could get would be 0. So technically that would work just fine. We know that's at least 3 standard deviations out of the way because of our success failure condition. So that actually works out pretty well. So we're going to go from 0 to 1/2, or 0.5. So this is all the possible probabilities that would predict a defeat from our samples, centered at 0.52 with a standard deviation of 2.5%. Put that in the calculator. I'll go ahead and do it for you so you can see just in case. So we go to second variables, which is distribution menu. The second one, which is normal CDF, stands for cumulative density function. Our lower limit, we're going to go from 0. Our upper limit, we're going to do 0.5, centered at 0.52 with a standard deviation of 0.025. All right, then hit paste and enter, and that's going to give us 21.2% essentially. So 21.2% chance that the sample that the newspaper gets from the random 400 people is going to predict that it's going to be defeated, which would actually be what we call a type 2 error, because we make the wrong conclusion based on the null or whatever, but we'll get into that later. They would fail to recognize that there is enough support for it to pass, and we believe it actually would pass if it was really 52%, but because of the variation, due to the lack of our sample size, we would have thought that there wasn't enough support for it, which is kind of interesting. That actually could have happened 21% of the time, so it's kind of cool. This is actually how statistics is used. That's why we have this thing called a margin of error, and so they would predict whatever they got plus or minus whatever the margin of error is, and as long as the margin of error is not containing the 50%, then they would be pretty confident with whatever alpha level they use. But we'll get into all that stuff, and that's why, yeah, this is actually a really good example of how polling is used and how stats and sampling distribution models are used in polling. So if you like the political stuff, this is how it's used all the time. All right, next one, 32. A restaurant anticipates serving 180 people on any given Friday evening and believes about 20% of the patrons will order the steak, essentially. How many of those meals should he plan on serving in order to be pretty sure of having enough steaks on hand to meet the customer demand? So being pretty sure means we're going to go within 2 standard deviations, because we would expect 95% of the time to be within 2 standard deviations. So I want to go 2 standard deviations to the right in order to make sure that I have enough. And it would be pretty unusual for anything to have more than 2 standard deviations from what I expect. All right, so how many do I expect? Well, 20% of 180, I guess I can put that in the calculator real quick. So 180 times 0.2, oops, so it's going to be 36, but whatever. So 180 times 0.2, yeah, 36. So I'm expecting 36, but I'm going to work with proportions instead of the binomial, which is like how many we're expecting out of 180, because that's kind of what we're in this unit. You can work with binomial, but we need to start working with proportions, so it's good. Now's a good time as any. So I'm expecting 20%. My standard deviation, this is our sampling distribution model of 180 for our sample size. So it's going to be 0.2 times 0.8, so P times Q, divided by our sample size of 180, and then I take the square root of that. So that's going to be caret 0.5, which will give me basically 3%. So centered at 20% with standard deviation 3%, so I can fill that in. I want to know towards the upper end, so that we had a higher percentage than we expected within 2 standard deviations up, going up would what is the trick on that? I have no idea. Anyway, that's what would give me what I would consider unusual. So going up 2 standard deviations would be 26%. So I would say that if I had more than 26% of my patrons who ordered the steak special, I would consider that unusual. So what is 26% of 180? So basically, how many steaks should I order or make sure that I have on hand? So 0.26 times 180, which is going to be 46.8, and we can't have 0.8 of a patron, so we'll round it up to 47. So if I basically do 0.26 times 180, it's kind of going from the proportion back to like a binomial, in other words, then I should basically say I need to have 47 steaks at hand. Now, what percent of the time would we expect to run out of steak? Well, that's going to be this with a z-score of 2, basically what's on the right side there. I want to find that area. So even if it really was 20%, there's still variation that could happen with a small sample of 180 people. And so to find that, we're going to do the normal CDF. So second distribution, normal CDF is the second one here. Centered, our lower limit is going to be 0.26. Upper limit, we're just going to go up to 1, which would be the highest proportion you could get is 1, right? Because it's a probability. Centered at 0.2 with a standard deviation of 0.03, and then hit paste. which would be basically 2.3%. So that's what I put in the calculator. So anyway, you can do as much precision as what, but basically 2.3% of the time I would expect to run out of steak on any given Friday, if I'm assuming that 20%, 180 people will be there and 20% of them will order steaks. As long as I had 47 steaks, I should be good. As long as you're okay with, running out of steak. Is this enough? If it's not, then you have to increase this. Just like decreasing your alpha level, but we'll get into all that stuff coming up shortly with our next unit. So, our next chapter. If you guys have any questions, let me know. If not, I'll see you guys later.